Welcome back to Chapter 3 of Principles of Mathematical Analysis. In this section, we ask two natural questions about the arithmetic of series. First, if two series converge, can we add them term by term? The answer is yes, and the proof takes only a few lines. Second, can we multiply two convergent series? This turns out to be much more subtle. We first have to decide what the product of two series should even mean, and that leads to the Cauchy product. Then we will see a striking example where the product of two convergent series diverges, a theorem of Mertens that rescues the situation when one of the factors converges absolutely, and finally a theorem of Abel describing what happens when the product series converges at all. Let's get started. Here is the plan for this section. We begin with some motivation, asking how far the arithmetic of limits extends to series. Then we prove theorem 3.47, which settles addition. Convergent series add term by term. Next, we define the Cauchy product and explain where the definition comes from, using power series. After that, example 3.409 shows that the Cauchy product of two convergent series can actually diverge. The centerpiece of the section is Mertens' theorem, theorem 350, which says that the product converges to the right value as soon as at least one of the two series converges absolutely. We close with Abel's theorem, which we state now and prove much later in Chapter 8, and then a short summary. Let's set the stage. Back in theorem 3.3, we proved that limits of sequences interact nicely with arithmetic if S sub n converges to S and T sub n converges to T, then the sums converge to the sum of the limits, and the products converge to the product of the limits. A series is nothing but the limit of its partial sums, so it is natural to hope that series can be added and multiplied just as comfortably. Next, let's see how far that hope carries. For series, the two operations behave very differently. Addition is easy, because the partial sums of the term by term sum are just the sums of the partial sums, so the sequence result applies directly. Multiplication is another story. The partial sums of a product series, however we define it, are not the products of the partial sums. In fact, it is not even clear at the outset what the product of two series should mean. We will have to choose a definition before we can prove anything. Next, here is a preview of what we will find. Here is the preview in the last bullet. We will adopt the so-called Cauchy product as our definition of multiplication. Surprisingly, the Cauchy product of two convergent series can diverge. Example 349 gives an explicit case. But there is good news. Mertens' theorem says that if at least one of the two factors converges absolutely, the product converges, and it converges to the product of the two sums. This is another place where absolute convergence, introduced in the previous section, proves to be the decisive property. Let's begin with the easy part, addition. Here's the first theorem, which settles addition completely. If the series of A sub n converges to A, and the series of B sub n converges to B, then the series whose nth term is A sub n plus B sub n converges to A plus B. Moreover, multiplying every term by a fixed constant C multiplies the sum by C. The key idea shown below the box is that the partial sums of the new series are exactly the sums of the old partial sums. So the arithmetic of limits from theorem 3.3 does all the work. Let's write out the short proof. The proof is exactly the key idea made precise. Let capital A sub n and capital B sub n denote the n, th partial sums of the two series. Adding them and regrouping, the sum of the two partial sums is precisely the n, the partial sum of the series of A sub k plus B sub k. Now both partial sum sequences converge to A and to B respectively. So by the arithmetic of limits, their sum converges to A plus B. The statement about the constant multiple is even simpler. The partial sums of the scaled series are C times capital A sub n, which converges to C times A. That finishes addition. Now we turn to the genuinely interesting question, multiplication. Let's pause and take stock, as the remark on the slide does. Two convergent series may be added term by term, and the resulting series converges to the sum of the two sums. The situation becomes more complicated when we consider multiplication. To begin with, we have to define the product, because there is no single obvious candidate. One could imagine multiplying corresponding terms, but that turns out not to reflect multiplication of the sums at all. The definition we shall adopt is the so-called Cauchy product, and as we will see on the next slide, it is exactly the definition that power series force upon us. Here is the definition. Given two series, we form a new sequence, C sub n, defined as the sum over k from 0 to n of A sub k times B sub n minus k. The series of these C sub n is called the product of the two given series. Look at the line below the box to see what this formula really says. The term C sub n gathers together every product of one term from each series whose indices add up to exactly n. So C sub 2, for instance, contains A sub 0 times B sub 2 plus A sub 1 times B sub 1 plus A sub 2 times B sub 0. Why group the products this way? The next slide shows the motivation. The motivation comes from power series. Take two power series, one with coefficients A sub yin n and one with coefficients B sub yin, and multiply them out term by term, the way you would multiply two long polynomials. Then collect the terms containing the same power of z. As the expansion on the slide shows, the constant term is A sub 0 times B sub 0. The coefficient of z gathers the two products whose indices add to 1. The coefficient of z squared gathers the three products whose indices add to 2. The pattern is clear. The coefficient of z to the abron n is exactly our c sub n. Next, one small step turns this into the definition. The last line of the expansion identifies the collected coefficients as c sub 0, c sub 1, c sub 2, and so on. Now set z equal to 1. The left side becomes the product of the two ordinary series, and the right side becomes the series of the c sub n. So the Cauchy product is precisely what formal multiplication of power series suggests the product ought to be. Of course, this calculation was purely formal. Whether the resulting series actually converges to the product of the two sums is exactly the question this section investigates. Before that, let's picture the definition geometrically. This picture shows all the products you can form from the two series arranged in an infinite grid. The columns are indexed by I, the index of the R terms, and the rows are indexed by J, the index of the B terms. So the cell in column I and row J contains the product A sub I times B sub J. The shaded stripes run along the anti-diagonals of the grid. the sets of cells where I plus j is constant. Each stripe is labeled at its lower left end with the term it produces. The single corner cell gives C sub 0. The next stripe of 2 cells gives C sub 1. The stripe of 3 cells gives C sub 2, and so on. The grayed out cells in the lower right belong to later diagonals. Summing the Cauchy product series means sweeping out this grid one diagonal at a time. Now, does this product behave well? The next example gives a startling answer. Let's set up the question precisely. Capital A sub n, capital B sub n, and capital C sub n are the partial sums of the two given series and of their Cauchy product. Suppose the two given series converge to A and B. We would like the product series to converge to A times B. But notice the first bullet. Capital C sub n is not the product of capital A sub n and capital B sub n. The product of the partial sums contains all products from a square block of the grid, while capital C sub n only sums the first few diagonals, which form a triangle. So the sequence result about products of limits does not apply, and the dependence of the product partial sums on the original ones is quite complicated. In fact, we will now show that the product of two convergent series may actually diverge. Here is the series we will use, shown in the orange box. Its terms alternate in sign, and their absolute values, 1 over the square root of n plus 1, decrease monotonically to 0. So theorem 343, the alternating series test from the section on summation by parts, applies and the series converges. But notice the first bullet. The convergence is not absolute. The absolute values form essentially the series of 1 over the square root of n, which diverges, since we know the series of 1 over n to the power p diverges whenever p is at most 1. Keep that in mind for later. The plan now is to form the Cauchy product of this series with itself, and watch what happens to the product terms. Let's compute the product terms. The first display shows the first few. The signs of the factors combine, so that every product inside the ANE group has the same sign, namely -1 to the EN. For example, the group for NN equal to 1 contains 2 copies of 1 over the square root of 2, both negative. The general formula appears in the second display. C sub En is -1 to the Ln times the sum over k of 1 over the square root of the product of n minus k plus 1 and k plus 1. There is no cancellation inside each sub n. All n plus 1 summons reinforce each other. That is exactly what will sync the series. Next, we estimate how big these terms are. Now the estimate. The identity at the top rewrites the product of n minus k plus 1 and k plus 1 by completing the square. It equals the square of n over 2 plus 1 minus the square of n over 2 minus k. Dropping the subtracted square only increases the value, so the product under the square root is at most the square of n over 2 plus 1. Taking square roots, each denominator is at most n over 2 plus 1. So each summoned in C sub n is at least 2 over n plus 2. Adding up the n plus 1, summons gives the boxed lower bound, 2 times n plus 1 over n plus 2. The graph shows this lower bound in red as n grows. It climbs toward the dashed line at height 2 and never comes close to 0. But by theorem 323, the terms of any convergent series must tend to 0. Here they do not, so the product series diverges. the product of two convergent series has diverged. Notice that both factors converged only non-absolutely. The next theorem shows this is the only way such a failure can happen. Here is the theorem of Mertens, with its 4 hypotheses listed in the red box. Hypothesis A is the crucial one. The first series converges absolutely. Hypothesis B names its sum A. Hypothesis C says the second series converges with sum B. And notice that for the second series, we ask only for plain convergence, nothing more. Hypothesis D just recalls the definition of the Cauchy product terms C sub n, so the setup is deliberately asymmetric. One factor is strong, absolutely convergent, while the other factor can be as fragile as the alternating series from the previous example. Next, the conclusion. And here is the conclusion. The Cauchy product series converges, and its sum is exactly A times B. In words, the product of two convergent series converges, and to the right value, provided at least one of the two series converges absolutely. Compare this with example 3/9. There, both factors converged only non-absolutely, and the product fell apart. Mertens's theorem tells us that one absolutely convergent factor is enough to prevent that disaster. Before diving into the proof, let's lay out the strategy. Here's the roadmap in 4 steps. First, we regroup the product partial sum capital C sub n, so that it is expressed through the terms A sub k of the strong series and the partial sums capital B sub k of the weak one. Second, we split off a main term, capital A sub n times b, which clearly converges to A times b, plus a remainder gamma sub n. Everything then reduces to showing that the remainder tends to 0. Third, to do that, we cut the remainder into 2 pieces at an index n, beyond which the partial sums capital B sub k are within epsilon of b. Fourth, the piece with small betas is controlled by alpha, the sum of the absolute values of the A sub n. This is precisely where absolute convergence earns its keep. With the plan in hand, let's carry out step 1. Step 1 is a regrouping trick. Write out capital C sub n as the sum of all the diagonal groups, as in the first line. Now, instead of reading this triangle of products diagonal by diagonal, collect all the products that share the same A factor. The terms containing A sub 0 are A sub 0 times B sub 0 through B sub n, which add up to A sub 0 times capital B sub n. The terms containing A sub 1 pair with B sub 0 through B sub n minus 1, giving A sub 1 times capital B sub n minus 1. Continuing, we get the second line, a convolution of the A terms with the partial sums of the B series. This expresses the complicated object through things we understand. Next, we feed in what we know about those partial sums. Step 2 isolates the main term. Define beta sub n as the error of the n Sethane partial sum of the B series, capital B sub n minus b. By hypothesis C, these errors tend to 0. Substituting b plus the error into each partial sum in our formula and expanding, the b terms collect into capital A sub n times b, and the leftovers form the quantity gamma sub n, the convolution of the A terms with the errors beta. Now the main term, capital A sub n times b, converges to A times b, which is exactly the value we want. So everything boils down to equation 21. The remainder gamma sub n must tend to 0. Intuitively, this is plausible, since the betas tend to 0. But the number of summons in gamma sub n grows with n. So we need to be careful. That is the content of the next step. Step 3 is the heart of the proof. First define alpha as the sum of the absolute values of the A sub n. This number is finite precisely because of hypothesis A. This is the one and only place where absolute convergence is used. Now, let epsilon be given. Since the betas tend to 0, we can choose a threshold n, beyond which every beta has absolute value at most epsilon. Split gamma sub n into two pieces, as in the display. The early betas, beta sub 0 through beta sub n, each multiplied by a late a term, and the late betas, which come multiplied by various a terms. For the second piece, each beta is at most epsilon, and the sum of the absolute values of the accompanying a factors is at most alpha. So the second piece is at most epsilon times alpha, a quantity we control. The first piece still depends on n, and the final step deals with it. Step 4 finishes the job. The first piece consists of a fixed number of summons, namely n plus one of them, with fixed coefficients beta sub 0 through beta sub n. The a factors in this piece have indices n minus n through n, which march off to infinity as n grows, and the terms of a convergent series tend to 0. So each a factor tends to 0. A fixed finite sum of terms each tending to 0 tends to 0. Therefore the limit superior of the absolute value of gamma sub n is at most epsilon times alpha. But epsilon was an arbitrary positive number, and alpha is a fixed finite constant. So the limit superior must be 0, which is exactly equation 21. The remainder vanishes, the main term gives a times b, and the boxed conclusion follows. The Cauchy product converges to a times b. One natural question remains, and Abel answered it. Here's the last result of the section, due to Abel. Suppose all three series converge, the two factors with sums a and b, and their Cauchy product with sum c. Then c must equal a times b. Look at the bullets below the box. First, no assumption of absolute convergence is made anywhere. Second, this answers the remaining question. The Cauchy product of two convergent series might diverge, as we saw. But if it happens to converge, it cannot converge to the wrong value. Third, we do not prove this theorem now. A simple proof depends on the continuity of power series, a tool we will only develop in Chapter 8. So the proof will come right after Theorem 8.2. Let's summarize what we have learned. Let's review what we covered. First, addition is completely unproblematic. Theorem 3.47 says that two convergent series may be added term by term, and the result converges to the sum of the two sums. Likewise, a constant factor can be pulled out of a convergent series. The proof was a one-liner using the arithmetic of limits. Next, the product. Second, multiplication required a definition. The Cauchy product, whose nth term collects all products of terms whose indices add to n. The definition is exactly what multiplying power series and setting z equal to 1 suggests. Third, the warning of example 3.49. The Cauchy product of the alternating series of 1 over the square root of n plus 1 with itself has terms that stay near size 2 instead of tending to 0. So the product of two convergent series can diverge. Finally, the two positive results. The last bullet collects the two positive results. Mertens's theorem. If at least one of the two factors converges absolutely, the Cauchy product converges to a times b. The proof split the product partial sums into a main term plus a convolution remainder, and absolute convergence tamed the remainder. And Abel's theorem, With no absolute convergence at all, if the Cauchy product happens to converge, its sum is necessarily A times B. The proof waits until Chapter 8. Once again, absolute convergence was the dividing line between good and bad behavior. In the next section, we will see this even more dramatically. We study rearrangements and discover that reordering the terms of a non-absolutely convergent series can change its sum to anything we like, while absolutely convergent series are immune to reordering. See you there.